So hi everybody, this video is specifically made for the broad oceanographic community, which strongly relies and uses the methods introduced in the notebook series. I've been getting lots of questions regarding the input, so the data input that we feed into the notebooks. And throughout all the notebooks, the input essentially was a grid velocity field. Now, in the oceanographic community, often you don't have direct access to the velocity field, but you do have direct access to the sea surface height profile. So basically, you have a scalar field, which is the sea surface height profile, and from that sea surface height profile, you want to extract structures. Now, of course, this sea surface height profile is directly related to the underlying velocity field using the quasi-geostrophic assumption. That's why in this video, I will go through the computation of the velocity field from the sea surface height profile. The folders, the notebooks are essentially inside. So of course we're considering 2D flows, and we're still in the regime, or we're still looking at AVISO data, so it's satellite data. However, this time the satellite data does not capture the velocity field, but it just captures the sea surface height profile. So you can see, of course, the MAT file, which is the MAT file we've been using throughout all our notebooks so far. And then you can see three scripts. So the first script, AVISO, which I call, is simply, so it gives a brief introduction to the AVISO data. And what it does is it simply shows how to import the velocity data so that it's in an array format. So if I run the script, then you can see that I've now imported the data which is stored inside this MAT file. And you can see that if I print, for example, the shape of the velocity, so of the x component velocity field, the shape of the x coordinates, so of the x dimension, and the shape of the y dimension, and also the shape of the time of the data, you can see that, okay, so the first one is simply the u, so it's the u array. And the first dimension is corresponds to the y component. The second dimension corresponds to the x component. And the third dimension is simply time. However, what I assume here, and that's very important, is that the units of the velocity field, so the units of u and v, of course, need to match the units of x, y, and t. So one common issue is, for example, that in oceanography, you download data and the velocity field is given in meters per second. However, the grid coordinates, so the spatial coordinates, are given in degrees. So for example, the longitude and latitudinal degree, and the time is not given in seconds, but it's given in days. So of course, if you then use the velocity field, which is given in meters per second, and input that to the notebook, then you will get nonsense results, because you're basically having an issue with the units. So you always need to make sure that the units of this u and v, so of the velocity field, of course, need to match the units of the grid coordinates, so of the spatial and temporal grid coordinates. So that's very important. I mentioned this because in oceanography, it's often assumed that the velocity field is, for example, given in meters per second. So what you then need to do is you need to convert this velocity field, which is given in meters per second, to degrees per day. Now, we don't need to do this for this MAT file because this has already been done. So the data you get from here is so the u and v here are already in degrees per day. But in case you download velocity data from some platform and the velocity data is in meters per second, then you would need to convert this. And I've actually appended a notebook which does this. So of course, there's this specific formula where u is simply the x and y component of the velocity field in meters per second. So u and v are, of course, the x and y component of the velocity field in meters per second. Theta is simply the latitudinal component. So of course, it depends on where you are in latitude. R is the Earth radius, and this is just, of course, p and some constants here, basically. And you can then feed, you can use this function here, which simply implements. So it does this conversion here, and as an input to the function, you give the x and y grid, so basically the longitude and the latitude, or the x and y component of the mesh grid. And then, of course, you also need to give the u and v in meters per second. And as an output, what you get So of course you do all these computations. This is simple. So this part here is simply this part here. And this function then returns the gridded U and V velocity data in degrees per day. Now, you need to do this if the velocity that you have is given in meters per second, and you need to convert this to degrees per day. However, what also often tends to happen is that the data you download is not a velocity field, but it's actually a sea surface height profile. So we now need to see how we can convert the sea surface height profile to the corresponding velocity field. As an example, the sea surface height profile, you can download it from the Copernicus website. So if I click on here, then you will be redirected to the Copernicus website. There, you will need to pick the data set which you're most interested in, which would be this global ocean, so which would be this data set. Of course, before you download the data, you would need to sign up. So it's of course free, but you will need to log in and register to the website. Then you can go up here. And yeah, that's actually now my login details. But then once you're here, and let's say you wanna compute, so you wanna extract the sea surface height profile, you would just need to go here. And of course, we don't want all the variables, but let's say we just want the sea surface height profile. And then you can pick a region. Let's draw a region on the map, which is, for example, this region here, not too big, not too small. And you need to specify the period. Let's say we want to do this for last year. Oops. And okay, let's do this over 7 days. So here we're basically now downloading the sea surface height profile from the Copernicus website over 7 days in this region we specified here. And we then, of course, need to click on download. So the download should start to happen now. This might take a while depending on your internet connection, but since we, of course, the bigger the data set, the more time it will take. But let's just wait a second. It shouldn't take too long in the end. Oops. So let me see for a moment. Yeah, so this is taking a bit now, but let's just wait patiently. Of course, I could skip this and not let you see this. Okay, so this is done now. Fair enough. Now we need to basically drag this. So you can see this file here in the downloads, and we need to drag this into the corresponding Aviso folder. So, and I just simply rename this to, let's say, SSH test. So this is now should be like a .nc file called SSH test. So now let's get back to our original script. Let's check whether this file we downloaded is in the folder. Yes, it is. You can see it here. It says SSH test. So the next thing we do now is, okay, we need to, of course, so this is the formula which basically converts the C. So given the sea surface height profile, which is simply this H, you can then convert it. You can then extract basically the velocity field, U and V, which is here in this formula, it's still given in meters per second. So we basically need to, because the sea surface height profile is of course given in meters. So once we have this, we then need to convert it to degrees per day. The function which does is it's called simply SSH to val, and it takes as an input simply the file. And the important thing is that it's a .nc file. So you need to extract it according to this. So in this way. Once you have extracted it, you need to, of course, define a bunch of parameters like the Earth's acceleration, radius of the Earth, etc. And then what you simply do is, of course, you simply iterate over time. You iterate over time, and then you need to simply evaluate the formula here and do the computation, which is done here. Of course, what we do is we interpolate the SSH. So since the C server state profile is just a scalar field, we just simply interpolate it, and with respect to theta and phi, where theta and phi are simply now our x and basically phi is our x and theta is our y component. And then this is simply the derivative of the C server state profile with respect to theta, so basically with respect to the y component, and this is the derivative with respect to phi. So with respect to the x component, we need the derivatives, as you can see here, because we need to compute them. So what we have then here is simply we have then as an output, so after this for loop, we simply have then the velocity field in meters per second. What we then need to do is we need to pass this velocity field in meters per second to this convert, so to this function here, which does the conversion of meters per second to degrees per day. And that's pretty much it. So as an input, actually, you don't need to care too much about it, but as an input, if this is your NC file downloaded from Copernicus, you just simply need to give this as an input to the function. And as an output, you get the corresponding X, Y components of the grid, the U and V velocity field, now in degrees per day, and also the time of the data. And if I run this, oh, actually, yeah, because this, I would actually need to specify. So our file is of course called SSH test. So I would need to pass SSH test here. Otherwise it gives an error, of course. And that's pretty much it. And I've saved this velocity field then in a mod file according to, so you can then simply use this mod file and input it then to the notebooks, as we've already done with the other velocity fields. And here you can, for example, see how. So if I were to plot now the extracted velocity field, then that's simply it. With that, I would like to thank you for your attention. And in case there are any questions, then please feel free to contact me.